Hello everybody, here program 123 again, and now we're going to learn how to do efficient greatest common divisor. But first we gotta learn what is the time complexity of computing a Fibonacci element. So remember that the Fibonacci sequence is that one that is 1, 1, 2, 3, 5, 8, 13, and so on. So, applying some mathematical analysis, we know that the ratio between every two consecutive numbers of Fibonacci is 1.618 and so on. We know that that is the ratio. It's an approximate value. If we make 2 times phi, we're going to get very close to 3. Not exactly, but very close. So we can generalize this as a geometric progression. Okay. The only thing that we gotta have in mind is this ratio. So remember that a geometric progression is that one in which the nth element is formed by the first times the ratio raised to the power of n minus 1. So applying some math, we get that n is equal to logarithm base r of a n, which is the nth element, plus 1. But remember that r is very close to number 2. So remember this, r is very close to 2. So we can approximate that this n is going to be close to log base 2 of a n. It is close, not exactly, but it's close. And in the range that we usually work in these competitive programming problems, which is 1 to 2 at 64, there are a little bit more than 64 steps, but it's actually an acceptable number of steps instead of 1000 or 1 million. Actually, for 10 to the power of 18, we get only 88 numbers of Fibonacci. So this is what we have to have in mind in order to understand the complexity of greatest common divisor. Here we are with Euclidean algorithm, which is the one that is going to help us to compute the greatest common divisor of two numbers. Okay, so basically it says that the greatest common divisor of a and b is equal to the greatest common divisor of the remainder modulo a of b and a. Notice that if a is greater than b, then on the first round you are going to swap values. I mean, you are not explicitly going to swap values, but the code itself is going to swap these values. That is the one thing that it is going to do on the first step. And then it is going to go over and over recursively to compute the greatest common divisor of a and b. Why did I mention Fibonacci numbers at the beginning? Well, because the number of steps that Euclidean algorithm makes in order to compute the greatest common divisor is equal to the number of steps you take to form a Fibonacci number. It's actually an upper bound, but the number of steps that you make in Fibonacci sequence is the upper bound for the greatest common divisor. Actually, the worst case of greatest common divisor is gonna be two consecutive Fibonacci numbers. In that case, you will perform n steps, being n the index of the number of Fibonacci in the Fibonacci sequence. Okay, so for example, if you have the greatest common divisor of 21 and 34, which are two numbers of Fibonacci which have index of 8 and 9 respectively, you are going to perform 9 steps to get to the greatest common divisor. That's everything we have to know about the greatest common divisor. But there is some other powerful tool that we have to understand with this greatest common divisor, which is the linear property of greatest common divisor, which is this one right here that says that a times x plus b times y, with x and y being integers, is equal to the greatest common divisor of a and b. We can also compute the values of x and y. We have no problem with that. How do we know the values of these two variables? But before we get started with the explanation, you may be wondering, what is this going to help us? Some of you may already know what the applications of greatest common divisor are, but what about the linear property of greatest common divisor? Well, let me tell you that this helps us a lot in finding solutions for geometric equations. We're gonna see that on the next video, but just have that in mind. This linear property actually helps us finding those solutions that are very valuable, because there are a lot of applications for the geometric equations, and we're gonna see them in more detail in a future video. You can see them in chemistry, for example, when balancing an equation, in economics, in network flow. There are a lot of applications for the geometric equations. Well, as a base case, what happens when you have already found the greatest common divisor? For example, when you get the greatest common divisor of 9 and 15, well, the steps that you're going to perform in the Euclidean algorithm is that 15 is going to be equal to 9 times 1 plus 6. Then 9 is equal to 6 times 1 plus 3. And 6 is equal to 3 times 2 plus 0. The steps you made were actually, you were first trying to find the greatest common divisor of 9 and 15. But then you changed to greatest common divisor of 6 and 9. And then you changed to greatest common divisor of 3 and 6. And our program runs another time this recursion, so you get to the pair 0, 3. So what happens when you have this pair? Well, it is obvious that the greatest common divisor is 3. Okay, so if you wanna know the values of x and y, then you have 0x plus 3y equal 3. So what is the value of x? We don't care about it. It can be any value because it is multiplied by 0. And y, obviously, it is obvious that y is equal to 1. So here we have our base case. When a equals 0, y is going to be equal to 1, and x is going to be equal to 0. So let's try to find the values of x and y for 3 and 6, for example. We are going to generate the formula to do it. We do not know these values of x and y, but we do know that it is equal to greatest common divisor of a and b. But this is also equal to the next step in the recursion. Let's call them x1 and y1 and y1 because they are not equal. Okay, how do we define b mod a? Well, do you remember this equation that says that n is equal to p q plus r? So remember that in this case q equals to n divided by p. So what is r equal to? Remember that r is the same as b mod a, or in this case it would be n mod p. Okay, so let's see what r is equal to. So we just move PQ to the other side, and you get R is going to be equal to N minus PQ. And what did we say that was Q? Well, R should be equal to N minus P times floor function of N divided by Q. So we can apply the same analysis to get the value of B mod A. Okay, so we do know the value of B mod A in terms of B and A. Okay, so we got to the answer that we needed. We needed to make the next step in the recursion. So since we knew the value of x1 and y1, we need to compute the values of x and y according to those other values. So what we did was to transform the right side into the left side. We got something like this. So let's see what we have learned in code. Okay, so here we have our code for greatest common divisor and for finding these factors x and y. Okay, so what we're going to do in our main function is to read a and b, and we're going to see if our implementation of greatest common divisor is okay, and then we're going to print the greatest common divisor, but at the same time we're going to get the values of x and y. Okay, so first let's analyze the function GCD, which is to compute the greatest common divisor of a and b. So we have two possible implementations. We have this one that I have commented, which is the recursive one, and this one that is not recursive. So for competitive programming, I would recommend using this one instead of this other one. Why? Because it is faster to code this than to code this while cycle and then return b. Now it is easier to just write this line and you're done. That's everything you gotta do. So I would recommend this one because remember, we're not going to have more than 100 steps for 2 to the power of 64. So if you want to calculate just greatest common divisor, then do that. And if you want to get the lowest common multiple of a and b, then you just have to return a divided by greatest common divisor of a and b, and all that times b. Okay, so we are going to also print the lowest common multiple of a and b. This is just for you to see the correctness of our code. Okay, now when you are finding x and y, well, we just have to apply the formula. Okay, so we have these variables x and y in the main function, and we're going to pass them to the function as references, so we can modify their values inside the function. Okay, and we're going to have these temporary variables in each of the calls to the function so that we can modify their value later. Okay, so that is basically what our code is doing. I am taking these values as references, I am modifying them, and then I modify the values that I should modify in this call according to the values that I have previously computed, and we just add the base case. When a is equal to 0, well, x is going to be equal to 0, and y is going to be equal to 1. We return the greatest common divisor, and that's it. So let's see the correctness of our code with the test case 9 and 15. So let's see lowest common divisor, greatest common divisor again, a, b, and x, y. Okay. Oh well, we had a mistake here. Oh yeah, it's because I'm declaring this function before the other one. So make sure you always code lowest common multiple after greatest common divisor, so you don't have this kind of errors. Okay, so the lowest common multiple between 9 and 15 is 45, and that's true. 9 times 5 equals 45, and 15 times 3 equals 45. Okay, so here we have a greatest common divisor, which is 3, and this 3 corresponds to this line of code. So you see how we are computing the greatest common divisor, and here we have it again, but in the other function. Then we get 9, 15, which are the values of a and b, and we get the value of x equal to 2 and value of y equal to -1. And that is correct, because 9 times 2 equals 18, and 15 times -1 equals -15, and 18 minus 15 equals 3, which is the greatest common divisor. And it's okay, our code has been implemented correctly. And that's it for today, you guys. I hope you enjoyed this video. I hope this video was useful for you. Share it with those who need it. Don't forget to subscribe and comment, and remember to stay home programming, and see you in another video. Bye bye.